Now, as we have seen the Ampere Circuital law, now we shall be trying to apply the Ampere Circuital law in order to find out the magnetic field produced by a current along a circular cylinder. Now, how shall it look like? So, for example, we take this circular cylinder likewise. Mind that the circular cylinder is in infinite length. Right? So let us check, say for example, this is the circular cylinder and this is of infinite length. We are just seeing a finite part of that infinite length circular cylinder. So over here, first of all, do observe that, say for example, this is the radius, right? And the radius, say for example, equals to capital R. Okay? And we wish to find out the B produced by I along this, which is the I or the current that is flowing along this circular cylinder. The I may be flowing, this circular cylinder may be a hollow circular cylinder or a solid circular cylinder, right? Now the I is flowing through it. For example, if we are looking at a point over here, then how will we actually treat it? Say for example, you are seeing the circular cylinder right from over there. But if you wish to see this circular cylinder from a very, very long distance, you will just simply see it as a straight wire. Because any straight wire is just like this, which is in turn actually a circular cylinder. Right? So, any point that is outside the circular cylinder, we wish to find out that what would be the value of B. There will be the several cases. So for example, at this particular point of P, we wish to find out that what would be the value of this B. So the first case what we wish to find out is that outside this circular cylinder, which means over here that the radius that we are considering is actually greater than R. So for example, this is the radius of this point. So we shall say that this radius over here is actually this, what is the distance between this P to the axis of the cylinder is simply greater than equals to capital R. Or we can take over here that the value of R is equals to capital A. Right? And we wish to find out the value of B with the application of Ampere's Circuital law. Now what the Ampere's Circuital law actually tells us about? The Ampere Circuital law actually tells us that first of all you need to define a closed region. Okay, not a problem. Let us define a closed region over here. So this is like a circle around this cylinder, right? This is A. So we can apply as we know now that the integration of the line integration of B is actually equals to mu naught I. Let us say this is mu naught I dash. Now over in this line integral, if the I is flowing along the entire cylinder, it means that within this total actual periphery or this region, it is going to get the total amount of I, right? So the total amount of I which is flowing through this circular cylinder is equals to I. I equal to total amount of current flowing in cylinder. And what is I dash? This I dash is basically equals to the amount of current bounded by the closed region, right? And over here, what is the amount of the current that is bounded by this entire region, or this red line, or this red circle? It is simply equals to the total amount of current flowing through the cylinder. So we can write this I naught now as I dash. So like I dash as I over here. So this will be simply equals to B multiplied by, now what will be the line integral for dl? The line integral for dl is basically equals to, as we have seen, the perimeter of this circle. Now this circle, as being the radius, is equals to capital A, so the perimeter of this circle will be equals to 2 pi capital A multiplied by 2 pi capital A will be equals to mu naught I. Or in other words, now we can say that the B is equals to mu naught I divided by 2 pi A. With this relation, we can actually see over here that B is inversely proportional to the distance of this location of P. Right? We have seen, because over C, B is over here and A is in the denominator. So B is inversely proportional to A. This is the first case when this point is lying outside this cylinder. No matter whether this cylinder is a hollow cylinder or a solid cylinder. The second case what we shall be discussing is simply about when this line will be on the surface of this cylinder, which means over here that R will be equals to capital R. This is capital R. When a point, say for example this point, say Q, is lying on the surface of it, so obviously we shall be bounding the region likewise, that this will go entirely and would come like this. The dotted line actually indicates that they are on the other side that is not visible of this cylinder, right? So over here, if we do apply this Ampere's circuital law, again we shall get it like this, equals to mu naught I dash. Now what is the value of the amount of current bounded by this closed region of this blue ink or this blue circle? Again, it will be having the total cylinder inside its periphery or region, closed interval or closed region, which means that over here again I dash will simply be equal to I, or the total amount of current that is flowing through this cylinder, irrespective of whether the cylinder is either hollow or solid. So this will be, which implies B multiplied by the line integral of dl over this region will again be actually equal to the perimeter of this circle. The perimeter of this circle with the radius of capital R will be equals to 2 pi capital R. 2 pi capital R equals to mu naught I, which implies that now we could write that B is equals to mu naught I divided by 2 pi capital R. Right? Now, let us take the third scenario. Say, for example, let us take the third scenario as inside a point which is inside this. Over here, if we do observe, if a point is inside, then obviously this R will be lesser than this capital R. How? Let us take, for example, a point over here. This point, right, inside this cylinder, which means, say for example, this is a point S. Let us draw a bounded circle so as to apply the Ampere's circuital law around that whole region, right? Now, if this R is less than R, as we can see that, say for example, we have taken this R equals to small a, along with the condition that this is hollow. This cylinder is hollow, which means that this cylinder is only made up of a conducting sheet of metal, right? We could put a hand inside it. This is simply hollow. So, applying the Ampere's circuital law over here, we shall get at as the integration or the line integral of B dl will be equals to mu naught I dash. Now what will be the value of I dash? Within this black encircled area, will you actually feel any current? No, because if it is hollow, which means that the current is being conducted by this cylinder only through its surface, the inner surface and the outer surface. Say for example like this, the current will be conducted on the outer surface and the inner surface, but inside it will simply be hollow, right? So we shall not feel any electric current inside. So I dash in this scenario will simply be equal to 0. And if the I dash is simply equals to 0 in this scenario, we shall find that the integration, line integration of BDL is equals to simply 0. Or we will find that B over here at this region is equals to 0. Right? Now we are coming for the fourth scenario as again we do take that this point is inside the cylinder, which means that the distance will be lesser than this capital R. Taking this distance is equals to A, but now this is a solid cylinder. Right? If we do take it for the derivation, the line integral of B at that particular region will be equals to mu naught multiplied by I dash. Now let us say for example this is a closed, like this is a solid cylinder, and over there in the solid cylinder, if we do find out this I dash, we will simply feel that this I dash is a bit lower, because if we are going to cut this solid cylinder from this, as being there is an inside a smaller cylinder of smaller radius, if we take it out, obviously there will be a current, plus there will be a current outside to this. So obviously we shall be getting a less current. So what will be the value of this I dash? The value of the I dash will simply be equals to, in this scenario, the value of, say for example, the value of I dash will be equals to the total amount of I was actually distributed in the total cross-sectional area of this cylinder. So, in unit cross-sectional area, how much I is present multiplied by what is the cross-sectional area we are taking. If we do that, we will find out that within this much cross-sectional area, how much the current is. So, the current per unit cross-sectional area will simply be equals to I divided by A, or the area over here will be equals to pi capital R square, multiplied by how much area we are taking, or the cross-sectional area we are taking. It is simply equals to pi A square, pi small a square. If we do look out, this pi will cancel out this pi, right? So, as we know over here, that the line integral of this dl along this inside or within the periphery of this black line, the line integral of dl will simply be the perimeter of the circle with the radius of small a, or it is simply equals to 2 pi small a. So that will be b multiplied by 2 pi small a equals to mu naught. This I dash now will be replaced by this value multiplied by I multiplied by a square divided by r square. Now if we make over here this term as 2 pi a, this will come as the denominator, so this a will cancel out the a square, leaving only a as the numerator, which means that we are going to find out the expression for b as b equals to mu naught I multiplied by a divided by 2 pi capital R square, right? So this will be the expression for the b when it is, this point is inside. Say for example, this R will be lesser than this capital R equals to a, but this is a solid cylinder, right? And if this is the scenario, we shall find that this b, what we have found out, is directly proportional to a. How? Because CB is in the numerator side, A is also in the numerator side. So now if we wish to find out the graphical representation of this, that how actually the B varies from point to point, such for example, we wish to take this axis as B, this axis say as the amount or the magnitude of the magnetic field, and on this axis we wish to find out as how it varies as per distance. Right? So we shall be finding out that if it is just that over here, it will be 0. The line will be directly proportional to A. It will reach a maximum point at on the surface where the value of B will simply be equal to mu naught I divided by 2 pi r, where this R equals to capital R, and this value of B will simply be equals to mu naught I divided by 2 pi r at this point, the value of B. After that, what will happen is that after that it will start decreasing, because B is now inversely proportional to A, which means that the more far we go from the cylinder, this B shall decrease, right? But this is inversely proportional to A, which means it is directly proportional to 1 by A. So the curve will now start like on this way, right? So this is the graph for a solid cylinder. Now if it is the case of, say, a hollow cylinder, over here, first of all, up till the surface, the graph will be just along over here. It will be 0, the value of B will be 0. Just as we reach on the surface, as R equals to capital R, this will be over at the point. And after we go away from the surface, it will be taking this relation that B is inversely proportional to A. So the graph will be like this, right? So we can say that particular this region, we do mean it for the region inside, and for particular this region, this is outside, and this particular point over here, we mean it that this is on the surface of the cylinder. Surface. Right? So this is all about that how we have used Ampere's circuital law in order to understand the B produced by the current along a circular cylinder, right? Where the point is outside on the surface and inside in the case of a hollow and a solid cylinder likewise. In the next lecture we shall be discussing about the toroidal solenoid.